All right, we are live. Okay, let me get the chat set up here. Okay, so essentially today we are going to be doing some assembly practice, RISC-V assembly. I just generated a practice problem set here from beginner to advanced, and we're just going to be furthering our understanding for assembly, essentially. Let me make sure everything's good on the audio side and everything. Yeah, it looks good here. All right. Alright, so let's start. Alright, so, okay. RISC-V register names. Just want to recap this. X0 is always hard set to 0. X1 is return address. X2, stack pointer. X5 to X7 and X28 to X31. Temporary registers so they don't save. They're just temporary values. The caller saves them. And X8 to X9, X18 to X27 are the saved registers. The callee is saving them. The function that gets called. And function arguments X10, X11, A0, 1. And then X10, X11 function arguments. And this is also return values. Okay. And these are like the abbreviation names. So yeah, I guess we can start. I'll probably come back to the reference if I need. Alright, so let's start with section 1 here. Alright, so we have arithmetic and register operations. So we're essentially writing a snippet that adds two integers together and stores a result. Alright, let's just start with that. Let me just get rid of this from earlier. Alright, so for that we need to load two values in. So in two temporary registers. So that means we will need to add I instruction. So add I. And we'll be storing it in T0. And we will be adding the X0 value to 12. So adding the immediate and storing that into T0. And also doing the same with temporary register 1. In this case, will be set. And we need so now we need to add those two together because we are computing the sum and storing it in register T2, temporary register 2. So this is just to add. Storing it in the destination register of T2, and we're essentially just adding temporary register 0 and temporary register 1, and this should be the value that's in it, and this is just the ending part to close it properly. So it should be this. We can actually check, right? We can actually check inside a compiler. So we don't have to have a function. Let's just have so okay, wait, it was 12, right? 12, and then I'll just like make it similar. So and this was supposed to be 7, right? And then inside T2 we store T0 plus T1, right? Essentially, we can look. I think this goes more in depth. Yeah, this goes more in depth, so it won't cover our practice part. So for the practice so far, this should be right. Oh, it gets trick. So that should be the right answer. We can move on to the second problem now. Let's see. Alright, so the second problem, we use an immediate constant value to perform arithmetic, and we don't need a second register, okay? So first storing the value 100 into T0, so the add instruction of T0, the temporary register 0, and we need x0 and storing the immediate value of 100 into that, and for our task. So write separate instructions for each. Store the value 100 plus 42 in T1, okay. Plus, okay, so, all right, okay, that makes sense. So we want add I in this case, and it'll be T1 that we're taking, and we already have the value of 100 in T0, so T0 and 42 is our immediate value. So essentially taking the immediate value, adding it to the value of the register of T0 and storing that in T1. And then they also wanted, okay, this one is add. I want to take a look at the instruction set again for a second. Okay. Alright, so we did the first two parts. So now store the value T0 minus 15 in T2. Okay, so this would be a subtraction. Or no, you can still do add I, but just we need to make it a negative value, storing a negative immediate. So since we can't do subtraction without two registers, so we need to have two. And then it would just be T0, and then having a negative immediate value of minus 15. Right, and then the last step, store the constant value 99 directly into T3 without using any other register. Okay, yeah, that's fine. So in this case, we need add I to temporary register 3, 0, and storing the value 99. Alright, that should be good. Yeah, seems like we got that. Yeah, there's no sub I instruction, so we can't do sub I. We have to do add I and then make it a negative immediate value. So essentially this stores a value of 100 into T0 and then stores the value of T0 minus 42 or plus 42 into T1. Then we're going here, storing the value of T0 minus 15 into T2. Then for T3, storing the value of 99 directly into there. So that should be right. Let's just see if we got the right answer. Let's just I don't have like the answer key or anything, so I'll just be putting it to Gemini to see if we got it right. It should be right though. Yeah, so that's right. It'll start getting harder later as we go down, so I don't expect it to be easy for the entire thing. Alright, now it's problem 3, bitwise operations. Alright, so bitwise operations work on individual bits of register, but it's able to perform the following operations using the values below. Following operations using the values below. Okay, so that's decimal for 202, decimal for 182, and that's just a binary value. So how are we gonna get this? Okay. So in the case of this, right, we need T0 storing that value, so I guess just starting out by doing an add-I, T0. And we can just store that value, so there would be 11001010. Same thing with this. Temporary register 1. So it would be 10110110. So I don't know if we can do it like this, but I'm pretty sure we can. So let's see if that's possible. Let's just continue on with the next part. Okay, so the next part, we need tasks storing T0 and T1 into T2. All right. So this would just be the AND operation. Since we're using two registers, I believe we can just use the value of just the AND here, bitwise AND, since we're doing arithmetic on two registers, T1 and T2, or T0 and T1. If we had an immediate, then we use AND-I, but yeah. So we use the AND operation. T3, right? Oh no, T2, and then storing T0, T1, which should be how it's put in, right? So AND operation, it does its operation on RS1, RS2, and stores it in that destination register. That's the format, and it looks like we do have that. So that should be right. Now we need to do OR operation. So we'll do OR. Is it all lowercase? Yeah, it is. So for the OR operation, we need T3 and then T0, T1, essentially the same thing. For exclusive OR. So temporary register 4, T4, we have T0, T1 again. Okay. Now for the next instruction, we need to shift T0 left by 2 bits and store in T5. So we're doing a left shift operation, which will be shift left logical immediate. I'm pretty sure it would be this one here, shift left logical, right? Okay, so that's just SLL, and we're storing that value in T5, and we're shifting T0 by 2 bits. So we need to store. Okay, well, we're doing it by an immediate value, so it'd be shift left logical immediate. It wouldn't be this one because this is doing it by a register, right? And in this case, we're just doing it by 2 bits, so we need to use the one here, shift left logical immediate, which is taking a value in a register, source register 1, and shifting it by the amount of bits in the immediate, and then storing that in a destination register. So essentially we need, okay, so we need our T0 value first, because you're shifting T0 left. Shit, my bad here. T0, then store in T5. Store in T5, and we're shifting left by 2, so the immediate would just be, it would just be 2, I believe, or would be 2, right? because I know it's like, I know it's a thing where it's like you can shift by 2, you shift in multiples of 2, so powers of 2. So this would just be a shift by 1, or no, it would be a shift. I'll say 2. I want to see if I can get it correct. Let's see. Right here, so in some context, a left shift by n is equivalent to multiplying by 2 to the power of it. Okay, yeah, so if we're shifting by 2, it would just be 1. Because we're shifting by that n amount, so it should be like that. And I think we did everything, so let's put into Gemini now. Let's see. If I got it right. Should be right. Let me get some water. Alright, so setup is correct. Loading the binary values. Correct. Here's slider. The prompt asks you to shift T0 by left by 2 bits, but your instruction currently shifts it by 1 bit. Okay, wait. Let me just do a query to find out. So it says that left shift by n is equivalent to multiplying by 2 to the power of n. So I assume that n is what we had in our snippet. So I got that by putting 1, we were shifting by 2 to the power of 1. I think he can clarify it for me here. You confuse the number of bit positions to shift with the mathematical. Wait, where is that? Oh yeah, number of bit positions to shift with the mathematical side effect of the shift. So it actually works. The immediate value you put in the shift left logical immediate instruction, it's a literal number of bits you want to move over. 10 to about 2 to the power of n. Let's just explain what happens to the underlying decimal value when you do that. So you're removing the bit spaces 2 to the left, your immediate value is simply 2. Okay, so the bits are actually what is actually changed. Like the value of the bits itself is multiplying by that value. But this is just the same as putting it in here as 2. So we don't need to actually change that value. Okay, that clears it up for me now. So I think I fixed the mic problem that I had a little bit. Like it doesn't have like the background fan noise anymore. Hopefully. I'll recheck the bot later to see if it's better. And then I'll probably keep the fan in this permanent position if that's better. I won't move it. So, okay, so we have... This is right, okay. Next. Okay, so we're moving up a section now. We're still in the beginner problem, so it still shouldn't be that bad. Okay, so... Section 2, memory access. So now we're loading and storing words. Okay. Write a snippet that reads a 32-bit integer from memory, doubles it, and writes it back to a different memory location. Okay. So when we read memory, we're using load keywords, and when we're writing memory, we're saving using the save keyword. I think I might have it backwards, but let's see. Okay, so let's take a look back at the thing, right? So for like something like load word, right? Storing the values and storing it into a register, whereas in save we're storing values to registers, and this would be the value in the register 2. values to registers and registers to values. That's like the way it is here. So essentially, if we go back here, okay, so reading a 32-bit integer from memory. A0 holds the address of source register, source integer. Was A0 back again? Like, I want to take a look. So A0 and A1 were function arguments, right? So, okay, so we're reading. So since we're reading to, we'd have to first use the load word since it's a 32-bit integer, so that's 4 bytes, and loading words is 4 bytes. So I assume it'd be load word. And the format for it, let me check again. So the format for it was load byte, load word, the memory value, the value in memory of RS1, the memory address, and then plus the immediate. So first we need a destination register though. And in this case, let's say A0, right? Then we need the offset of RS1, just like we have here. So we have RS1, which will be, what would be our RS1 though in this case? What would be the RS1? I guess just A0, right? So we're just loading it from A0. But we're having an offset of a certain amount, so doubling it, right? So would it be 2 of A0? Something like this, I assume. Let's look at the hits, right? So use offset equals 0 when the register already holds the exact address you want, but it doesn't though, right? We cannot multiply directly by 2 with the mul instruction here. Yeah, we can. Shifting or adding a register to itself does. Okay, so let's give the problem here to Gemini's need to see if I'm on the right track. Okay, so however, there are 2 quick tweaks you need to make to that first line before moving on to math. Look closely at there. Use offset equals 0 when the register already holds the exact address you want. 2 bytes past your target address. see. Alright, so he wants us to change this to t0, so we don't rewrite, overwrite, and then just change this to 0. And then, okay, so let's try and think about what it means to shift by that, to double it, right? So shift left logical by immediate, right? Would it be a shift left logical immediate? Because that would be similar to what we were doing before by changing the bits so that we do it in values of 2 to the power of n. So, okay, so would it be like, we could sort this in t1. So let's say t0. And shifting the value of t0 by 2 because, well, no. We need it by 1. Because doing that by 1, that would essentially mean the actual value would be shifted to the power of 1, which is 2, which is what we want. So I assume that we have to shift it here. So no, we don't. We can't. Okay, yeah, that makes sense because this is not a shift. This is like offset. So we're not actually shifting anything. So we're just accessing from there, and then save it, right? So save word, store word, not save word, store word, and that would be the register that we have, so the T1 value, the T1 register, right? And then storing that into the offset of RS1. So what we wanted earlier, so we're storing that into A0, 0A0. I believe that is what we wanted. Let's see. I still believe we're missing something, but I'm not exactly sure. Correctly grab the value with source address. You brilliantly applied the left shift. Okay, so we did the shift right. Okay, the storing it, okay. Okay, so you just overrode the original integer back at the source address, so we don't want that. We want to hold the address of destination register. DST. Oh yeah, okay, so right, so that's what it did say in here. A1 holds the address of the destination register. So we do want to change this to A. That would be the end of the problem. So that one did require us to think a little bit. Let's see if we can do the next one. So that's right. Let's do the next one. Alright, so now we're accessing array elements. So arrays in memory are stored as contiguous words, yeah. To access element I of an integer array, you compute the byte address as base plus I times 4, since each int is 4 bytes. Okay. So the base address plus I times 4, which is where it is in the, which element it is in the array, and that's the byte address of it. So in this case, we need a base address of an integer array, A0, okay, and then the index I, a non-negative integer, will be stored in A1, so, okay. So now we need to load array I, the I value of the array, into T0. Okay, so we need to shift by 4 times 4. So last time we did it times 2, which was 2 to the power of 1. So now we need 2 to the power of 2. So left shift by 2. But what are we left shifting though? So integer array, right? So I guess just load word. Same thing with load word, but this time we have an array. So it would need to be A0, and then same thing here, right? Since we'd access the first element of A1 essentially. Not A1, A0, sorry. A0. But let's store that in like a temporary value. Like a T1 value, right? Now we want to shift to the left, so let's just store that in a T2 value. And I assume we just need to shift that by 2 because that would mean the value of the bits are multiplied by 4, which would work for the addressing I times 4. So then we're definitely doing something wrong here. Yeah, definitely doing something wrong. Base address of an integer. Okay, so index I is A1, right? So I guess there's no need to really load anything, right? So I guess we can start off with the shift left logical. Or I'm not really sure. Yeah, right, bro. The next question here. Just to see what's like I'm not really sure what it means to like access the element. Hey, what's up, KZ Mans? How you doing, bro? Okay, so I'm not really sure exactly how we're approaching this. I'm doing pretty good, man. Just doing some assembly practice. Okay, wait, so yeah, so the shift left logical is multiplied by 4. Grabs the very first element of the array, and then your shift left logical multiplies the actual value by 4. For array access, you have to calculate the exact memory address before you can use the load word instruction. Let's walk through sequence. Okay, so alright, so shift index I. Where did I get those practice problems from? I got it from Claude. I'll actually show you. So if you go to Claude, right? Let me show you like the prompt I used. So I just asked it to give me a doc file that gives me a bunch of practice problems for the whatever I'm trying to do, and it literally just gives me a doc. It's actually amazing. It can do that for pretty much anything, like, and it can make it the doc as long as possible. It can make it like 20 pages of like just pure practice problems. For this case, it's like 17 pages of problems. So yeah, Claude's a goat. Alright, so it looks like they're just doing the shift immediately without actually storing it. We don't have to load a value at all. So we don't need this at all. We just can shift it automatically from A0 itself. We don't need to actually load it. Or no, A1. Why is it A1 though? A1, okay, we have to shift we're shifting the I value, and our I value is stored at A1, so makes sense. So okay, then we're adding the offset to the base address, which add instruction, yeah, wclod, bro, wclod. All right, so adding that offset to the base address. So I guess we just need T2 and add that and the base address, which would be A0. So we're just adding the offset, or in the problem it's base address plus I4, so let's flip that around. So base address and T1 as we had before. So now we have the add part. Now we need to load it. So loading the word, so loading the 32 bits. And it says to store it into T0, so temporary register 0. Not exactly this every day. I'm just starting this assembly practice now because I have a project that deals with it. So I'm just trying to build more on my knowledge of this stuff. Because I've run into like a kind of a roadblock in my project. I need to read some more stuff, so I'm just doing some practice before I get back to that project. So T0. Okay, so loading T0, the array of the index of I, so which would essentially just be T2. Right. Let's take a look. So word, memory address. I feel like we're missing something here. You don't know much about RISC-V assembly, but I just want to ask how useful RISC-V ASM is. Yeah, it's pretty useful depending on what you're trying to do. This one's RISC-V is open source, so you can actually like publish stuff on it if you wanted to. But there's like other instruction set architectures like ARM, x86, MIPS. Essentially, just like if you want, you can just find any book. Like this one is what I'm going over is this one. Computer Organization and Design, RISC-V edition, but there's like many editions. There's an ARMS edition, there's also like a MIPS edition, so you just gotta look at what you're doing, depending on your goals. Okay, so that's... Okay, so are we accessing NXI here? I think this is fine, but it's not a register. Well, it's a register plus an offset, so there's something I'm missing here. We need an offset value of that, so, but... I feel like I'm missing something. What are your goals, KZ Mint? Like, what are you trying to do? So... Oh yeah, he's right. Wait. I made a mistake here. Add instruction only takes register values. It doesn't take offsets, so we can't have the statement at all. It won't compile. So we can't have an offset. So it just needs to be A0. But then the offset goes here. I believe, like within T2, we offset by the amount. Yeah, okay, so I just mixed it up. I just mixed up the offset. So essentially, that's right. Yeah, it looks to be right. Let's just go over it. Let's just figure out. Second year in electrical engineering. Nice, man, nice. Doesn't have to do with like hardware and like stuff very close to the computer. I'm pretty sure like most like EE people who like CS do like embedded systems or hardware programming, like systems programming like this. Eventually you want to make your own RISC-V CPU. Nice, man. I'll show you the project I have so far. Yeah, it's really interesting, bro. Computer architecture. I find it much more interesting than like regular stuff like backend and front end. So let me open up my project. It's also on GitHub too. GitHub in the description. So, alright, so essentially what I have here is a decoder and an interpreter. So starting off, it grabs a binary value, so it asks the user for binary string, 32-bit binary string, converts that into an integer, so like just a set of bits in an integer form, and then basically it gets all like the layout of bits, because you know for each bit string, let me show you, each bit string has a layout like this to actually identify what instruction it is. So it identifies what instruction set it has, and then we have a switch case statement here that identifies which instruction it is depending on all the values it gets from the different layouts of the bits. And that's for the decoder, right? So it basically just, if you put the bit string, it tells you what it is. For the interpreter, I had to actually make like memory addresses and actually like read and write to register itself to actually like tell you what register values are stored when you have an instruction. I guess I can do a little bit, like show you here. Yeah, that's the thing. I like software stuff and computer architecture, so I wanted self-learn stuff. Yeah, you can definitely self-learn stuff. Like I have the book itself, I have like notebook LLM, so like every part I just have like quizzes that get generated for me and flashcards and stuff, and then also like lectures online. If you don't feel like reading the full book, you can also just look at lectures. It's pretty good too. But yeah. Alright, so for this, alright, so this one has different modes. So the decoder, so let me just get like a random bit string. I'm just asking for random bit string. Give me a random 32-bit string from that is an add I instruction. Hopefully it actually gives me something. Alright, so I don't know if MIPS, I don't know if it's like pretty sure it's mappable, pretty sure the same works. No, it's not, so let me get it for RISC-V. I really thought they were mappable, but I guess not. I guess it's a bit different. Okay, they're really not. Okay, they're not gonna give me the bit. Okay, apparently. So I'll just show a different part. I'll just show a different part, which I can actually show you immediately. So the interpreter. All right, so I have a file here. So the binary file, which has the instruction loaded in already. And this basically just does the instruction and stores it into the register. So it shows a direct image of all the registers and what was written to it and what was not written. It still has a lot of work to do. I only started this project like 2 weeks ago. Like literally 2 weeks ago. I've been doing it every day on stream. But now I've run into a roadblock where the knowledge gap is getting different. So I have to keep practicing and learning more. So once I read more, I'll get back to that project. But yeah, basically most of this is written by scratch from me. I wrote it all on stream. You just found me on YT homepage? Nice, man, nice. Also called opcode? What do you mean? Like opcode is part of the instruction format. Like each layout of bits, so like the lower bits are always going to be, like bits 0 to 6 are always going to be the opcode. Then destination register. Func3 specifies what exactly their operation is, so if it's like an add, subtract, and instruction, so on. Source register 1, which is the other register that you're doing arithmetic on, and then the immediate is usually like a shift or a value that, like a constant value that you're adding, depending on the instruction. Yeah. So yeah, that's basically the project. Now I think we should get back to the actual assembly practice. Yeah, essentially a software implementation of the RISC-V CPU, yeah. It's gonna be like an emulator once it's actually finished, like a full-fledged emulator, but it still has a lot of work to do. I'll just like keep writing to it and then I'll keep updating my GitHub for that, so. Alright, so this is done. This is done, right? Okay. Let me just run through this real quick. So shift left logical immediate. So temporary register 1, we're shifting left by 2, but the value we're multiplying by 4 because the value is multiplied by 2 to the power of n, so 2 to the power of 2 is 4. And we're shifting the A1, which was our base, the index. Then adding the base address value with our offset that we had from the shift and storing that in T2, and then loading the word at that address, which is pretty much, yeah, we can move on. All right, section 3, branching and control flow. All right, so nah, you're good, man. Nah, you're good. We're just chilling. I don't have like a deadline or anything, so I can just answer any question you have about anything. But I'm still relatively new, so like if I don't know something, I'll probably say I don't know. Okay, branching and control flow, right? Okay, so all right, this is where it gets a bit more difficult now. So we have branch if equal. We have the branch instructions. Branch if not equal. So this is basically our if statements, if and else statements, but in an assembly version. All right, so write a complete code block that computes the absolute value of a register. Oh, did the music stop? All right, back. I didn't know the music stopped. All right, so let's get back to that part. Okay, so temporary register 0 equals some signed integer. Could be positive, negative, or 0, okay? Okay, so the absolute value integer. So if it's positive, that would just mean that it'd stay the same. But if it's negative, that means we'd have to get it to the positive version of itself. So we'd have to add to it a certain amount to get it to that value. So let's try. So in this case, we need to check if the branch is greater than or equal to 0. So our signed integers, so we're checking t0, right? So t0, and then what would our second value be? I guess just we're checking it to x0, which would be 0, because x0 is always hard-coded to 0. So if our value is currently greater than or equal to 0, then I guess we'd continue, right? The last part of the branch of greater than or equal to is always going to be a jump to the next section. But what do we need to really jump to here? I'll just keep that there for now. Okay, so now here, branch is less than. So if our t0 branch is less than x0, you need to do a certain thing. I had to think of what that certain thing is though. Okay. Okay, but I think okay. You college student too? Yeah, I'm a second year student. Yeah, so okay. So assembly always goes step by step, right? So if we get this, we want to skip over this so we don't get to that part. So okay, I think I kind of get it. So in this case, we need like some type of thing that we're jumping to, so we can call it like, need a label. So let's make a label name. Let's make it, we'll call it less. No, we don't want to call it less, we'll call it more. So if we get that, we jump to more, and then we will, inside of more, we will have our thing. In this case, we just need to have the value of t0, since we don't need to modify t0 at all because it was already greater than or equal to 0. So we can just keep the absolute value as the same value. So let's look at the hints here. So branch, okay, yeah, that's what we're doing, using a branch to skip the negation step. Branch to done. Okay, let's call it done. So essentially, I don't think they want us to implement the logic here, right, for that. I'm not exactly sure if they want us to implement the logic here. What happens if we're just falling through though? Yeah, this is why I wanted to do the practice, because I need to like solidify my knowledge for this stuff that happens in these cases. Writing the code for that in C++ is different than actually handling it here. So I need to actually make sure I understand it here to level up this. So this is like a nice skeleton of it right here. So we need to understand where to go from here, which is what I'll ask Gemini to see what we can go forward for. I need to give it the context of it. You don't always need to, okay, right now's condition, okay. Right, okay. So this one is, oh yeah, this is kind of redundant here because since we already have this, if it's less than, it will just fall through, but if it's greater than, yeah, so we don't need this, okay. That's what was confusing me. I didn't know what to do with the less than or equal to, the less than part, because I didn't know if you need to branch to somewhere. Okay, that makes sense. Okay, so, but do we need to implement anything after? Wait. Okay, I see. Okay, so essentially want to have a value that we can manipulate at any time. So we want to load the value of t0 into t1. So in the case of this, if branch is greater than or equal to, we want to skip to done. So we can write that. Or we can write the logic first for the less than. Alright. So for the less than part, right? So if we have like a number like -12, to get it to the positive version, we need to add twice of that amount. So we need to add 24 to it to get it to +12. So we need to shift the value by a certain amount. How much do we have to shift it by? Or wait. Are we able to shift it like? Store the shift into, we can store it into T2 like this. Shift's less logical immediate, right? So we'll take the value of T1 and shift it by are you able to do -1? Let me write this down. Let me do it in a calculator. Hold on. No, that wouldn't work. So what are we? I feel like we need a shift, but I actually just don't know what type of shift. Or we don't need a shift. Okay, wait. Yeah, I don't understand this problem. Like, I understand like the context of it, I just don't know how to implement. So let's see. We'll concede for this problem, and we'll note down what we need to do for next time. Alright, so copying the value into T1, branching if it's greater. Okay, yeah. Negation. Okay, this is what I don't understand. Let's see. Subtracting 0. Oh, wait. Okay. Subtracting 0 minus the value of T0, which was what we had earlier. Because if, okay, so because if the value was like, let's say negative 12, so 0 minus of minus, okay, I see what they're doing. So that would make it positive 12. Okay, I can't believe I didn't think of that. Okay, that makes sense. That makes sense. I was thinking of it too. I was thinking of it way too hard there, which I shouldn't have. So it's essentially just subtraction. Like that. So, but the done block, did they say anything for the done block? Done block, we just exited the sequence. So the done block would just have this stuff in it. Yeah, I mean, that makes sense now that I look at it. Okay. We'll note that for another time. We'll probably do it in a couple more problems and then we'll probably wrap up. How much is there? So by the end of it, okay, wow, all right. Write a function Sterling that computes the length of such a string, not counting the null terminator. Okay, that's gonna be, that's quite a jump. That's in 7 problems. Fibonacci, cursive factorial. Okay, so it kind of like ramps up pretty quick from here. Wow, okay, so, all right, let's just continue with problem 7. All right. Oops. Alright. Write a snippet that finds the larger of 2 integers and stores it in a result register. Okay. So let's first get these two values set up. We can store them in a temporary, so say they say what register? No, okay, so alright, so we'll store it into T0. That'll be our first integer, which will be stored into temporary value. And then temporary value 1 will store our A1 value, which is our second integer. Then we can find the larger of the 2 integers. Okay, so branch of greater than or equal to. So if our first integer is greater than our second integer, oh, it's T0, T1, T1, T2, T0, T1. So if it's greater than or equal to, wait, your code must handle a case where they're equal as well. Yeah, so what would we do if it's equal? Let's see. So I guess, yeah, okay, so we want to structure it in a way such that we can do it. So this one will be branch of less than. So if it's less than, let's just send it to a place. Just call it less or something. So that happens, it will go here. If not, if it's equal or greater, it will fall through here. So now we have to do the case where it's equal to. So branch if equal to. So after, if it's false to this, it will fall to this. So now we have to do it if equal to. So branch if equal to T0, T1. You can call that equal. So now this will move to a place called equal, and then do the code there. But if it's neither of these, if it's greater, then it will execute the code that's following. And we want to store the max of the two values. So if it's greater, right? So that would mean that T0 was greater. So that would mean we need to store the value of T0 into our A0 register, I believe. Just as it shows. Wait, so this is going from a register to value, register to value. And this is a value to register, register to value. So it's gonna be this, right? I believe it would be like this if it's greater. In the case that it's less than, maybe something like T1. But essentially just be the same here. If it's equal, what does it say to do if it's equal? I actually don't know what to do if it's equal. We're storing the max of these two, right? So can't you just store any of them? What happens if it's equal and you have a max? And I guess just nothing, right? Because you can't really do that. So I guess this should just be it. And we can check if that's correct. I can check if that's the correct implementation. I probably got something wrong, but we'll see. We'll see. And yeah, I think after this one, we'll probably be done with the stream. We did 7 today. I don't know if we can do the next 7 tomorrow because that's like, these were all easy problems. So like tomorrow I'll probably do like 3, maybe 4. Because it will get harder. So the time it takes to complete a problem will take longer. A few syntax rules and end up overcomplicating the situation. Oh, yeah, we did. Okay, wait. I messed up right here. Add I only takes immediate values, not register values, so that's automatically wrong. If you want to copy the registries, move, or just add. Well, I'm not trying to use pseudo instructions. Yeah, not my bad. Adding is for registers. Add i's for immediates and registers. So yeah, okay. So that's the problem fixed right there. What else? Means the register, not RAM. So use the store word instruction, writing data out to the computer's main memory RAM. Oh, okay. If A0 is already the biggest number, or if they're equal. Oh, okay. Since A0, okay. I see. A0 is already the first integer anyway, so if the first integer is anyways the larger one, so we just need to simplify this. Don't need this part. Now we just want the ending call here. But if it's less than, if T1 is greater, that would be different, so. It would just be, what, like T1 is. It would just be that, right? Yeah, that would be right. That's, yeah, okay, so that's the right answer for this one now. We overcomplicate it again, so yeah, that makes sense now. We just need to think about it in a better way. In a less complicated way. We need to actually look at each parameter and actually do it properly. So yeah, the next section will be loops. I just want to take a quick look at it before we go. So this would be using JALR, I'm pretty sure. No, not JALR. JALR is for functions. It'd just be using these ones, yeah. Okay. Yeah, that makes sense. All right. So we'll try and implement some more problems tomorrow, but yeah, I think I'm gonna turn in for today, and it was a good session, but yeah.